Your tea, professors.
Did you bring the sugar?
Of course, Professor.
Very good. Thank you.
It's not going to get any sweeter, you know.
What are you on about, man? Of course it will.
Your tea is not going to get any sweeter. You keep putting in sugar, but it's not going to get any sweeter.
Well, yes, it will. Add more sugar. There's going to be more solvent-solute collisions, therefore more dissolving. Therefore, it's going to get sweeter.
But Puddleby, you've reached saturation, man. Your tea is at equilibrium. Adding more sugar now will only means more will settle to the bottom of your cup. You see, not only is the rate of dissolving increased, but so is the rate of crystallization. Do you understand? It's at equilibrium. Both rates are the same. Here, I'll show you what I mean. Your tea can be considered an equilibrium system. We can represent it like this.
Yes, I know. Solid sucrose plus water makes dissolved sucrose, or aqueous sucrose. So what are you on about, man?
Puddleby, you've added at least 15 teaspoons of sugar to your tea. After about the 10th one, the rate of solidification is equal to the rate of dissolving. You see, your tea is at equilibrium. It's not getting any sweeter. The sweetness, man, is constant.
You mean like an equilibrium constant? I'll show you about that. Nurse Carter.
Yes, Professor Puddleby?
Nurse, I'd like you to listen to this and see if I'm making myself clear. I'm going to show you a typical equilibrium system. Now, if we look here, the little letters represent the numbers to balance the reaction equation, and the big letters represent the reactants and the products. Now, I'm going to use all of this to write the equilibrium law expression for
hydrochloric acid iron 3 oxide equilibrium system. Allow me. According to the equilibrium law, which is the equilibrium constant is equal to the product of the equilibrium concentrations of the chemical products divided by the product of the equilibrium concentrations of the chemical reactants, where each concentration is raised to the power of the coefficient of each species. Keep in mind, it is always the products divided by the reactants. So it would apparently seem, in this case, that the equilibrium constant is equal to the product of the equilibrium concentrations of each of the chemical products, in this case, iron 3 chloride and water, divided by the product of the equilibrium concentrations of each of the reactants, hydrochloric acid and iron 3 oxide, where each concentration is raised to the power of each species. In this case, squared, cubed, and to the 6th.
But you've overlooked something, Nurse.
That we've included liquid water and the solid iron 3 oxide?
Splendid. Carry on, Nurse.
All right. I did say apparently. Now, the fact is, the equilibrium law expression for the reaction that you've just given does not look like this. Let's consider liquid water. Now, the concentration of water is constant in aqueous solution, so it is combined with the equilibrium constant and doesn't appear in the equilibrium law expression.
That is the point I was trying to make, Nurse.
But what about the iron 3 oxide solid?
Now the concentration of a solid is also considered a constant. It is combined with the equilibrium constant, and it also doesn't appear in the equilibrium law expression. So what we end up with is this as our equilibrium law expression for that equation.
Ha ha! So solids in product or reactant form and liquid water are never included in equilibrium constant expressions? What do you think of that, Puddleby?
Well, I'll tell you, Higginbottom, I think Nurse Carter knows her way around equilibrium law chemistry.
That's for sure.
How about that tea?
Oh, good idea.